Hello, welcome to the next part of our unit on magnetism. In this unit, we're going to look at the magnetic force acting on a moving charge. And to begin that, I want to ask a question. We saw in the last unit that a current carrying wire causes a force on a magnet. For example, in Ørsted's experiment, this caused the compass to rotate, to deflect. Is the opposite also possible? Can a magnet cause a force on a current carrying wire or on a moving charge? Because remember, all a current is really just charges moving through a wire. And hopefully you think about this answer and you come up with yes. You might even remember that there's a Newton's law involved here. The top one is we have a force on a magnet by a current. The bottom one would be a force on a current caused by a magnet. If you look, the cause and effect, if you will, are reversed in these two things. So these are a third law force pair. So yes, a magnet can cause a force on a moving charge. Now, the magnetic force and magnetic fields in a lot of ways, they're just weird. They're very different from what we've seen in the past. In order to properly calculate the force due to a magnetic field on a moving charge, we need to make some definitions. So we're going to have a charge moving with a particular velocity in a magnetic field. And let's say that magnetic field is at an angle like this, where this is an angle theta relative to the velocity. Then the magnitude of the magnetic force on that moving charge will be how big is the charge multiplied by how fast is it going, in what size of a field, and then there is this oddball factor sine theta. And weirdness happening. So remember, the sine of 0 is 0, and the sine of 90 degrees is 1, meaning that the magnetic force is as big as it's going to get when the charge is moving perpendicular to the magnetic field. It also means that the force will be 0 when the charge is moving in the same direction as the magnetic field. So summarizing that, the force will be 0 if the charge isn't moving. So if V is 0, there's no force. The force is 0 if it's moving in the same direction to the magnetic field. Okay, so illustrating this second point, if V is this way and the magnetic field points this way or it points that way, that's going to give us a force of 0. And then the force is going to be as big as possible when the charge is moving perpendicular to the field. So if the magnetic field points to the right, the force will be as big as possible if the velocity is towards the top of the page, towards the bottom of the page, but don't also forget about that it could be coming out of the page or going into the page. If you are not familiar with this ladder symbology, remember this looks like the tip of the arrow and it looks like it's coming out at you. You're seeing the tip of an arrow being fired at you. This looks like the fletching on the arrow, so that means it's moving away from you or into the page. So now the electric versus the magnetic force. Remember, F equals QE was the electric force. F equals QVB sine theta. So things that are different here. This is going to accelerate in the direction of the field. If it's a negative charge, yes, it goes opposite, right? This is going to cause an acceleration perpendicular to the field. This one can accelerate from rest. This one, if V is 0, then there's no force. So if you stick a charge at rest inside a magnetic field, nothing will happen. Something else has to get it moving. So there's a lot of differences between these two forces. The direction of the magnetic force is determined by right-hand rule B. Again, I go over right-hand rule B in the last part of this unit. I will do just this one example here. Okay, so right-hand rule B is for finding the force on a moving charge. For this one, you put the fingers of your right hand in the direction of the velocity, then rotate your fingers so that they point in the direction of the field. So basically they're 90 degrees to your palm, if you will. And then your thumb is going to give you the direction of the force. For this combination shown, the force, at least at first, will be downward. So let's do a couple of quick calculations and examples. So we have a 3 coulomb charge moving at 4 meters per second at an angle of 30 degrees to a 6 Tesla magnetic field. Okay, well, I'm going to let the magnetic field be going up like this. And there's my 30-degree angle. So F equals QVB sine theta, which is 3 coulombs times 4 Tesla times, not 4 Tesla, sorry, 4 meters per second times 6 Tesla times the sine of 30 degrees. Sine of 30, you might recall, is 1/2. So 3 times 4 times 6 divide by 2 is going to be a force of 36 newtons. For the next example here, we want to calculate the angle. So we bring out F equals QVB sine theta again. I'm going to solve first for sine theta, which will be the force divided by charge times velocity times field. The force, we are told, is 50 newtons. Q is 4 coulombs again. V is 3 meters per second. And B is 6 Tesla. This multiplies out to being sine theta equals 0.694, which means theta is 43.98 degrees. Okay, if a negatively charged particle enters a region of uniform magnetic field directed perpendicular to the particle's velocity, will the kinetic energy of the particle increase, decrease, or stay the same? So first, let's think about a negatively charged particle with a velocity entering a region with a magnetic field. Okay. By right-hand rule V, fingers in the direction of the velocity, rotate your hand so that you can move your fingers to a 90-degree angle and point along the magnetic field, 90 degrees to your palm, I should say. Your thumb then gives the direction of the force. By right-hand rule B, the force in this case will be out of the page, but this is not correct because it is a negatively charged particle. The right-hand rule gives the direction of the force on a positively charged particle. To get the direction of the force on a negatively charged particle, we've got to flip it around. So instead of pointing out of the page, it will point into the page. Okay, that doesn't answer the question, But it does get us to the answer to the question, because we can look and see the velocity is to the right, the force is going to be into the page, which means V is perpendicular to the force. The velocity is perpendicular to the force, and as you might recall, when this happens, when V is perpendicular to F, velocity changes direction, but does not change magnitude. If the velocity is not changing magnitude, then the kinetic energy will not change, so the kinetic energy stays the same. I mentioned a minute ago on this slide that at least at first the force will be towards the bottom of the page on this particular particle. Why doesn't it always stay that way? So let's look at this example where I have a charge moving upward, a positive charge, and a magnetic field out of the page. At this instant shown, the force on this particle would be to the right. But because there is a force to the right, that means this is going to change direction. So a little while later, it might be moving in this direction. If you again do the right-hand rule, you will find that the force is now going to point this way, and it's still going to be changing direction. And it will just keep doing this. So the path for this looks like a circle. And we have an object that is moving in a circle at constant speed, which means that the net force on that particle takes on the centripetal form, which you might remember is the mass times the centripetal acceleration, which can also be written as mv squared over r. Because the velocity and force are always velocity and the field are always perpendicular, sine of theta will be 90 degrees. I said that wrong. Because they are always perpendicular, theta will always be 90 degrees and sine of theta will be 1. So mv squared over r will equal charge times speed times field. Remember, sine of theta is sine of 90, which is 1. And now I can solve this for the radius of the circle. R equals mv divided by qb. This process of a charge moving in a circle or circular path in a magnetic field is the basis of a mass spectrometer. Let's do a quick calculation of this concept. So we have a 3 coulomb charge moving with a 3 coulomb, 2 kilogram mass charge moving in a circle with a radius of 3 meters at 15 meters per second. So here is the circular path. I'm told the radius is 3 meters. I'll let the velocity here be 15 meters per second. I want to know how big is the magnetic field. So R equals mv over qb. Rearranging that, the magnetic field is going to be mv divided by q times r, which is 2 kilograms times 15 meters per second divided by 3 coulombs times 3 meters. And that works out to be a 3.33 Tesla field.